So it's my great pleasure to introduce Joan Bruna, who is an associate professor at Courant Institute, New York University. He also has an appointment with the Department of Computer Science and Department of Mathematics and the Center for Data Science. He belongs to the CILVR group and to the Math and Data group from 2015 up until 2016. He was assistant professor of statistics at UC Berkeley and part of Berkeley AI Research. Before that, he worked at FAIR, Facebook AI Research in New York. And even before that, he was a postdoctoral researcher at Courant Institute. He completed his PhD in 2013 at École Polytechnique, France. Before his PhD, he was a research engineer at a semiconductor company developing real-time video processing algorithms. He did a master's at École Normale Supérieure de Cochin in Applied Math, MBA, and a BA and an MS at UPS, Universitat Politècnica de Catalunya, Barcelona, in both mathematics and telecommunication engineering. For his research contributions, he has been awarded a Sloan Research Fellowship 2018, and an SF Carrier Award 2019, a Best Paper Award at ICMLA, and the IAA Outstanding Paper Award. And today he's going to be telling us about mathematical aspects of neural network approximation and learning. So Joan, the floor is yours.
Okay, thank you very much, Nazir. Very nice introduction, and thank you for inviting me here to this seminar. Typically, I always like to mention my background, like mountain light background, but I guess that here I cannot compete. I see already some backgrounds that are more spectacular than mine. So anyway, so yeah, today, as Nazir said, I'm going to be talking about some of the work that I've been doing alongside of some of my colleagues. So I'm just going to acknowledge them here. Zhengdao Chen and Aaron, Sami, and Luca are PhD students of my group. Grant Rotzkopf is now assistant professor at Stanford. And Eric van den Eyden, whom probably you know, is my colleague at Courant as a professor in applied math. Okay, so probably here, even though it's a applied math colloquium, by now everyone is aware that we are in the area of deep learning experimental revolution, meaning that many problems and many domains that were just before, like less than 10 years ago, problems that were supposed to be kind of the boundary of what we could do with computational methods. Now these networks are starting to surprise us without a stop, right? So they start to do very well in computer vision applications, but now recently not just limited to computer vision and speech processing and maybe text processing, but now we see that more and more many problems in computational science, they also start to be quite remarkably well processed by these kind of deep learning set of techniques. And so at the end, if one wants to, as a mathematician, try to even like set up the problem, and first thing is try to describe, okay, what are these methods, right? So in essence, the essence is actually quite simple to describe, right? So at the end of the day, what we see is that we have some very high dimensional data that clearly contains very complicated structures. And so these methods, these deep learning methods, they really break with the traditional way in which we extracted information from these models, where before we carefully had to understand very well the physics of the problem to compute these features, right, to extract the right features. So these deep learning architectures, they just replace these kind of handcrafted features by some data-driven representation. And so the way this representation is obtained is by basically just looking at first order methods like gradient descent. And so the pipeline of deep learning of course, enables for the user to introduce some structure into this representation, for example, by incorporating physical structure. But the question really, the main question really remains is to understand when, how, and why. So what are the conditions where these deep learning systems can really efficiently approximate functions in high dimensions? And so the talk is really going to be focused on what we call the supervised learning. So this is kind of maybe the first stop in trying to understand some mathematics about the problem. And so in this setup, we have, of course, the first ingredient is high dimensional data. And here throughout the talk, I'm going to assume that the data has, of course, an input and some label. And so I'm going to assume always through the talk that the label, this yi, is obtained through some unknown function f star that one wishes to approximate, to learn from the data. Of course, the other ingredient is to have some function approximation, to have some model that is trying to hopefully predicting the x from the x to the y. And this model, you can think it as a space of functions that map this high dimensional space to some, just to simplify things, to the reals. And we can think about these models like, for example, the space of functions that you can express with neural networks of using a certain architecture. And we are going to also assume that one has an access to some notion of complexity, right? So we can associate to every hypothesis F a certain quantity, like a complexity, that we can use during training to choose what is the best hypothesis. Then, of course, we have a loss, like a means to evaluate how good is a hypothesis. So as is like standard in machine learning, the most of the trouble comes from the fact that there's a discrepancy between the loss that we care about, which is the test loss, like this population loss, the expectation over the data distribution of the difference between our function or approximation and the target. But we can only use algorithmically an empirical version of this loss, which is the replacing the expectation by a sample average over the data. And so the algorithm, like the paradigm to understand or like to find this hypothesis is what's called the empirical risk minimization, where in the formulation that I'm mostly being concerned about this talk, really tries to find a hypothesis f hat such that we are able to minimize this empirical functional, while in a set of hypotheses that has small complexity, right? So think that you introduce some kind of target complexity, and we're going to find what is the functions among that ball that have the smallest possible empirical loss. And so the starting point, like the mathematical setup or like the statistical setup of this problem, what we the first stop is really to rely on to try to understand how well is this algorithm going to perform. What we do is that we try to express the error, like the regret, against the best possible hypothesis in the ambient space in terms of like fundamental sources of error. And so this is following this very classic decomposition of error that you can find, for example, in the works of Léon Boutou and Olivier Bousquet. We can really think about the decomposition of error in terms of three main sources. The first one is the term here is really penalizing us for designing functional spaces that are wrong, right? In the sense that if we have a space of hypothesis that requires a lot of complexity to approximate the function that we care about, we are going to pay a big price here. The other source of error really comes from, again, from what I said, like the statistical error, like the price to pay to be optimizing the wrong function, like to be optimizing the empirical function, the empirical loss rather than population loss. And this is also something that we need that puts some pressure in how to define these spaces of functions. We're going to define spaces of functions that in some sense, they are not too big, right? That do not grow too much with respect to the dimension. And the last one, and it's by no means the smallest one, is the computational error, right? Like the optimization error that penalizes us what is our ability to solve this empirical risk minimization. And so the key of like the key mathematical question is how can we define a framework where we can control simultaneously these three sources of error in the high dimensional limit? And so why is this problem interesting to a mathematician? And the main reason why I would say it's interesting is because there's a very strong curse of dimensionality that kind of plagues all of these three sources of error. So in the sense that if we try to plug in this framework spaces of approximation, spaces of functions that come from, let's say, the classical approximation theory that were naturally defined for low-dimensional problems, we see that there's some kind of fundamental mismatch. In the sense that if we look for example, these hypothesis spaces that contain functions that are Lipschitz, like just a very weak notion of regularity, then we see that the size of that space is just blowing up too quickly with dimension, right? And the classic result from, let's say, Ulrich von Luxburg tell us that the sample complexity, right? If I want to identify a Lipschitz function from that space, I will just need an exponential number of samples, right? Like this illustration. If you think like as this sphere has more and more dimensions, if I want to identify just say like a function on the sphere, and the only thing I tell you is that this function is smooth, locally smooth, the only choice where you can approximate it well is to sample the sphere everywhere, right? To cover the sphere, to create the sphere. On the other hand, if you just try to work if instead you try to enforce maybe a bit more global regularity on the function, for example, asking that the target function is maybe in the Sobolev class, we have basically the same problem, unless the number of derivatives that you ask the function to have is basically linear with dimension, which is something that is not very realistic in the high dimensional limit. Think about this D as something of the order of millions. So this kind of sets the stage of the talk. That is, which functions we can hopefully hope to learn in this high dimensional regime that somehow go beyond this like disappointing trade-off that we have here. Amongst these functions, are there ones that are interesting that involve neural networks and that can be learned efficiently with gradient descent? And moving forward into the wish list, can we actually understand this question? What is the role of depth in this question, right? So how is the depth in the neural network going to help us with these trade-offs? And of course, the last stop in the wish list is deep networks that have some physical structure, right? As I said before, the physics structure of the problem here should not be forgotten. So in the talk today, of course, we are going to just try to do like an overview of we're going to do some zoom in a couple of snippets, but probably we are not going to be able to go all the way to the end. But I'm going to be focusing a lot in kind of the first stop in the problem is to look at the first instance where neural networks can probably go beyond these simple function spaces, which are captured by neural networks that have a single hidden layer, like this single hidden layer neural networks. And we are going to describe some optimization properties in these networks. And then in the second part of the talk, I'm going to describe extensions, right? How can we go beyond this space of functions that are determined by shallow neural networks? And before I continue, let me just mention that if anyone has any question or something, just please interrupt me or use the chat. I mean, it's Friday afternoon, so we can keep it informal. So just please don't hesitate to interrupt me. Okay, so a single hidden layer neural network, for those of you who have never seen it before, in fact is a relatively gentle set of hypotheses, because the functions that are in that I can express with a single hidden neural network, they really look like sums of simple functions. And here simple, we express this through the notion of a rich function. So rich function is a function that is defined over high dimensional space. But the first thing that it does is project the high dimensional input to some line, right? Basically, it chooses like it has a direction that is parameterizing, is basically projecting the input into one direction, and then applying it, passing it through an activation function. For example, this kind of sigmoid here. And so a single rich function is not a very interesting object. So this class of shallow neural networks are obtained by basically plugging like linear combinations of these rich functions. And so in this setup, we have three main parameters of the problem that we are going to be keeping throughout, which is the number L, the number of data points in the problem, in the training set, D, that is the dimension of the input, and N, which is the number of neurons that we use in this approximation. Okay, so to understand like how this architecture relates to the space of functions, we can look at maybe the envelope, right? So let's look at the ensemble of all the functions that can be expressed with a shallow neural network. So this naturally leads us to functions that can be expressed as just an infinitely wide, like an infinitely wide shallow neural network, where these functions are, one way to understand them is really to think about this as a gentle generalization of an object that is pretty familiar, which is think about this activation function, this unit here, as being the complex exponential, right? So if this was a complex exponential, this is nothing else than trying to express a function f in terms of its inverse Fourier transform. And so, not surprisingly, because here we are just replacing this activation function by something a bit more general, we kind of inherit, we can recover all of the nice things we know about approximation properties of Fourier representations. In particular, through, this is a classic works from the 90s, we know that as soon as this activation function is not a polynomial, then these approximations, right, are dense in the space of continuous functions, right, under the right topology. Nothing very surprising at this point. The question really is how can we actually now use this integral representation and define interesting spaces of functions? So the first thing that we can do is to look at our integral representation as before, and we can put here a fixed probability measure. So think about this as some kind of like a base measure over the space of features, and then consider all the functions that I can express by putting a kind of a transform version, like a, like the equivalent of the Fourier transform, to be square integrable. So here we have a really, we really are building this space from using some Hilbert structure. And so in fact, the right terminology, like the space that we obtain here, has actually the structure of a Hilbert space, and it's called a reproducing kernel Hilbert space. And so the kernel of this space of functions is explicit, and this is the properties of that space were developed and studied in this very nice paper by Francis Bach a few years ago. And so this space of function is appealing, is interesting, because it has like a nice, rich Hilbert structure, which means that we can understand pretty precisely all the questions about generalization. We can understand quite precisely questions of approximation using the theory of random features, the random feature expansions. For example, this work by Rahimi and Recht. And also we can understand very well optimization, right? So it's Hilbert structure is typically associated with things that are relatively easy. And so the downside here is that this Hilbert structure comes at a high cost. And the cost is really approximation, right? So these spaces of functions are not very big, right? So we again have this course of dimensionality that we saw before in the case of pseudo-F spaces. So only the functions that are very smooth are in the RKHS. And so, let me just mention here that there's a very modern and active area of research now in the theory of deep learning that tries to really close the bridge, like that borrow a lot of ideas that go from kernel theory to neural networks, mostly started like revived by this nice paper from Arthur Jacot and colleagues in this neurotangent kernel. So what is the alternative if you want to really go, try to overcome this lack of approximation of these RKHS spaces? What is the alternative? So the alternative is to somehow, instead of relying on this fixed probability measure, to let this probability measure or the space of features to be trainable, to be adaptive. And so the natural normalization here is to consider the mass, like the total mass of the measure that we consider is finite. So this is in technical terms, this is like the bounded variation. Like we look at the random measure of the measure, and we look at all the functions that we can express by integrating a measure that has finite random measure against the unit. And so actually this space is no longer Hilbert, but it's still like a Banach space. So we can still compute this complexity that I described before. And in fact, it comes by different names. So one interesting name is actually the Baron space. So that's a name that was coined by Wayne and Yu in honor of Andrew Baron, who in the 90s really studied a lot the properties of that space. And so that space, just by direct application of Jensen, is strictly larger than the previous one. So it's like, it has better approximation properties. And it has actually an interesting statistical advantage, namely that it can adapt, right? So here we are really moving from the Hilbert space that is kind of L2 flavor to L1, right? Which is something that is associated with the total variation. So as you might be familiar with all the theory of compressed sensing and L1 recovery, L1 gives us this adaptivity, right? The ability to adapt to find features that are useful for a particular observation. So here we have the same, again, in this work by Francis back, there was this very nice analysis that showed that this space has the ability to adapt to the low dimensional structure of the input. But of course, the downside, or like the question here, is that how can we actually officially find functions in that space, right? So how can we solve the empirical risk minimization if we are trying to do it in that space? Okay, and any questions so far? Good. Okay. Okay, so for this, we are going to now make an analogy between the neural networks of these shallow kind, like the shallow neural networks, and particle systems. And so if we, again, we assume that we have the setup where the target, the ground truth, is some unknown function f star. And so if we try to set up this empirical risk minimization for shallow neural networks, so again, shallow neural network is parameterized by, so every neuron has its own set of parameters. So we have n neurons. We have this big vector of parameters that is theta1 to theta n. And just for simplicity, I'm collecting both the input weight to the neuron and the output weight to the neuron into a single parameter, right? So this is also called as a kind of a lifting, right? So I'm just associating both the input and the output weights of the neuron as a single parameter. And now you can think about this parameter theta as being in some d-dimensional space, or d+1 dimensional space. And you can think it in your mind as a particle, right? It's like every neuron is just one point in that space. And so the function, now I'm going to just apply this normalization, and this is going to be, of course, apparent why I'm now, instead of doing the sum, I'm doing the average, but in terms of representation doesn't change anything. And so if I write the L2 regression laws, or like any general convex laws, with the norm that is associated with this F1 space, the Baron space, I end up with a empirical risk that I can express it like this. And so what we know about this empirical risk in this model is that in general, it's going to be a complicated object to study, because as soon as this unit is nonlinear, this objective function, right, is going to be completely non-convex, right? So we know that this problem is actually hard to analyze. In particular, it's hard to say anything positive about this problem. An alternative, like one way to overcome this challenge, is again rely on an idea that has been very useful across other areas of optimization and physics, is to re-parameterize the problem and to lift it into a different space. And so here, what we are going to do is, instead of trying to express this problem in terms of the positions of these particles, right, we are going to now introduce a new object, which is the empirical measure of where that is tracking the location of these particles, right? So we are going to introduce a new measure. In that case, it's like the empirical measure, and we are going to rewrite the energy in terms of this new object. So now, if you go out to this formula and you express this function in terms of this empirical measure, you see that almost by definition, there's a linear dependency. There's a linear relationship between the function and the empirical measure. So which means that thanks to this linear relationship, now the empirical risk minimization, if we express it now in terms of this new object, has the nice, there's a nice convexity that pops in, right? That emerges just because of the fact that now this object here is going to be convex in the measure, and this regularizer is in fact linear with respect to the measure. So the natural question really is now, okay, now let's try to see if our training algorithm, right, that again, the training algorithm, the computer is going to store the weights of these neurons, and it's going to use gradient descent. How does the training algorithm look like in this new measure domain, right? The space of probability measures over the space of parameters here. And so if we now look at the particle gradient, so the gradient that you feel at every particle, at every neuron, you can actually express it. So this is the kind of the Lagrangian gradient. You can really express it as evaluating the gradient of a certain velocity field. And the important property here is that this field, like this potential, so this is the field. So this field is a gradient of a potential function. And the important property here is that this potential function is itself a function of the measure. You can still write down formally the gradient that you see at every particle as evaluating, again, the gradient of a potential. And so just pictorially, imagine that you have this domain, this d-dimensional domain, and given the current state of the system, I have an empirical measure mu, and this empirical measure mu determines a potential on that domain that has a certain gradient, right? It has a certain velocity field. So when you put a particle in that domain, it's going to feel a velocity, right? It's going to feel that there's some force that is pushing it. And so, in fact, for general systems that where the general time-dependent measures mu t, when we try to understand how a measure evolves under a time-varying velocity field, this is a system that is well it's well understood in statistical mechanics and different areas of mathematical physics, and it's known as a continuity equation, right? So you can understand the continuous time behavior of this system of how the measure evolves through a partial differential equation that is just corresponds to the fact that there's a certain conservation of mass, right? So this divergence equation is just expressing that at every point in the domain the mass is preserved. And so in fact an interesting property, and again it's a consistency, is that in fact this partial differential equation can be understood as a gradient flow of the same objective that we had before, but now we express it with respect to the measure. Of course, there's one important distinction here, is that now we are studying a gradient flow in a space that is the space of measures. And in particular, we can show that this gradient flow, this is a gradient flow with respect to a particular metric in that space, which is called the Wasserstein metric. And this is the theory of understanding these Wasserstein gradient flows is really it's quite sophisticated, and there's very nice references, for example, this work by Ambrosio and others. So at this point, I just want to bring home the fact, and let me also mention that these equivalents, like observing that the gradient dynamics of a neural network, shallow neural network, can be understood as Wasserstein gradient flows, was actually pushed. This idea was developed simultaneously by several works a few years ago. In particular, the groups by Andrea Montanari and Song Mei. Also, there's some work by Leonid Shiza and Francis Beck, and also some of my colleagues, Grant and Eric van den Eyden. So at this point, what we are just saying is basically translating a problem, right? So the original way of thinking about the problem is this Lagrangian perspective, where we just track the position of the particles. So here we are faced with a complicated non-convex problem, but we are in an Euclidean domain, and we are in a finite dimensional domain, right? The dimension of the domain grows with a number of neurons, right? But it's always finite. But here we are expressing the same problem, the same system in a Eulerian domain, where we are trading off things, right? So we are gaining convexity, but we are presumably, creating new complications. In particular, now that the dynamics are going to be gradient with respect to a non-Euclidean metric, in particular the Wasserstein metric, and we are, of course, in this infinite dimensional space. So let's try to see if there's still some benefit on going into the Eulerian perspective. So one of the first important benefits is that in the Eulerian perspective, we have access to what we call this mean field limit. And again, let's try to understand intuitively what this mean field limit is doing. So the way I initialize the problem is that I'm going to draw at the initial time. I'm going to initialize the network with neurons that are drawn IID from a certain distribution. Let's call this distribution mu bar. Okay, that's what happens at the initial time. And then the system is going to train following, again, the particle dynamics, right? Like the standard algorithm that you would run in the computer. So that's going to follow, again, a trajectory in the space of measure that is going to evolve somewhere. So the natural question you would ask is that what happens as I put more and more particles in the system at time zero, if I increase the number of neurons? So we know that this empirical measure that is happening here converges weakly to its corresponding distribution mu bar. So naturally, one could ask the question, well, if I initialize the same PD, but I change the initial condition from the empirical measure mu0 n to mu bar, I will have a different trajectory. And the natural question is to understand to what extent these two trajectories are going to converge one to the other. So in fact, what one of the main outcomes of these works was that in fact the trajectory, the empirical trajectory, converges to the mean field trajectory in the limit where the number of particles goes to infinity, and in the case where this blue trajectory does converge in time, then the limits commute. So now we have what would be equivalent of the law of large numbers, right? So it's like in the limit where I sample more and more things, this kind of random, like the empirical object that is this purple trajectory converges to its mean object, right? Which is the blue trajectory. So the key question, of course, is to understand, to quantify the fluctuations, right? As the standard pipeline is that first one establishes this law of large numbers, then the next step is, can we get a certain sense of a central limit theorem, right? What is the size of the fluctuations? And here, let me just mention that, of course, the convergence, the real relevant convergence questions, they involve both convergence in time. So one would like this gradient flow to converge to the minimizers of the empirical loss. And the other one is, of course, the convergence in the number of particles. Okay, so first let's just discuss briefly about the global convergence of this mean field limit, right? So convergence in time to the minimizers of the loss. And so again, here we are, we are paying a little bit the price of having to study gradient flows in a metric that is not Euclidean. So in an Euclidean world, if I give you a convex function and you do gradient flow on a convex function, you are going to get to the global minimum, right? Just because of just by direct consequence of convexity. But here in a Wasserstein metric, that's not necessarily the case. In the sense that if one looks at the stationary points of the dynamics, right, like the stationary points of the partial differential equation I described before, they are not necessarily in one-to-one correspondence with the global minimizers of the energy. And the reason is that in the Wasserstein geometry, one can actually, it's like, one can think about this as a space that has boundaries, right? So whenever the mass, the measure becomes singular, the support of the measure becomes singular, one stops being able to argue about what happens in the complement, right? So you lose the ability to see what happens with the loss outside where you are. And so, in other words, the stationary points of the flow, they correspond to measures mu star, such that the potential, like the gradient of the potential, is actually zero in the support, right? So the potential is piecewise constant, and one can say that it's constant in the region of the support. Whereas global minimizers, they really are something a bit stronger, right? So not only this gradient has to be zero in the support, it actually has to be, like the level have to be the same for every point in the support, and outside the support, I need to certify that the functional derivative of the first variation of the loss has to be non-negative outside, right? So in a sense, one needs to be able to bridge the gap between the conditions here and the conditions here. So there's basically two different strategies right now in the literature to try to bridge this gap. The first one is to modify the gradient descent to make it a little bit more regular. So one way to do that is to add noise in the dynamics in the same style as one would do like a Langevin dynamics, right? So and this is something that was analyzed and studied in this paper by Song Mei and Montanari and Nguyen. And so once we put noise in the dynamics, we are able to change the PD into a PD that becomes a bit more elliptic, right? So in other words, that now the noise in the dynamics enforces the measure, like the distribution over the measure over parameters, to be very regular and to have full support, right? So this ability that the problem that we need to control what happens outside the support somehow disappears. And the other main technique that is the other main tool that is used in another work by Leonid Shiza and Francis Bach is to leverage also another property, structural property of the problem, that is the homogeneity of the unit, right? So if one studies functions that are homogeneous, so if it uses units that are homogeneous, then it's essentially one can relate properties that relate to the gradient, the properties that relate to the function, right? The homogeneous function, there's a link between the gradient of the function and the function. And so using this homogeneity and of course some more like refined analysis, one can also use like established global convergence. And here, let me also mention that we, together with Sami, Grant, and Eric, we took this idea and made it a bit more general by replacing the homogeneity again by a different change in the dynamics that uses what we call unbalanced transport. But the idea is essentially the same. Okay, so just as a summary, I mean, we under some conditions we can indeed show that there's convergence at the mean field level, but of course the mean field limit is a very non-quantitative object, right? It's something that holds when you have infinite number of neurons, and most of these results require having a measure initial condition that has full support, that is very regular. So one question that we were asking again is how can we go beyond this result and understand the size of the fluctuations? And this is a work that was led by Zhengdao and was presented last NeurIPS. So one important observation is that if one uses the Baron space like a regularizer, for example, the L2 of the L2 norm of the weights, one can obtain a space of functions like a space of measures where we can easily obtain approximation by sampling. So in other words, if you give me a function from that space, right, so that's associated with a certain measure, we can approximate this measure by sampling from mu0, right? So in other words, we can go the other way, right? So if you give me some measure in that space, I can always approximate it by sampling IAD copies of the measure, and the size of like the error can be easily quantified, right? So the error is exactly corresponding to the statistical rate, like the Monte Carlo error. Okay, so what controls the approximation error here is, so we know that the squared error is inversely proportional to the number of particles, and in the denominator we have exactly the variance of the unit, right? And the variance of the unit itself is controlled by what we call this Baron norm of the function, right? But that's not that important. So the question, of course, is that whenever we do this approximation error at time 0, the natural question is that how does this error evolve as training, right? So in other words, the dark blue curve here corresponds to the idealistic dynamics, the mean field dynamics for which we can maybe hope to get some guarantee of global convergence. So there's some guarantees that if this mu0 is a certain type, then this curve is going to converge to the global minimizer. But now we are going to make we're necessarily going to make an error by sampling. So we are going to indeed, the algorithm, the computer can only follow the light blue curve, right? And the question really is to understand how does this initial error, that is really the Monte Carlo rate, how does this error evolve as we train, right? So in mathematical terms, we're interested in understanding this quantity here. So a natural baseline, like if one had to guess, a potentially good guess is to say, well, let's try to complete this diagram, right? So instead of first sampling and then evolving, I can pretend that I can cheat, right? So I can follow the dark blue line at any point, and then at any point in time, I can decide to sample from this measure mu-t. I can sample n particles from this measure. And by the same argument as I did before, the error that I get by sampling n particles at that point is going to be proportional. The price to pay is going to be again at the same Monte Carlo scale, and I'm just going to replace the variance of the unit, like the variance of the measure at time 0, by the variance of the measure at time t. So this, of course, is a unrealistic, it's an unrealizable model, right? Because this object here would require me knowing mu-t, which is by the whole point of the argument is that we cannot follow this line. But think it as a kind of a mathematical object. So it turns out that this baseline is actually the right baseline, right? So what we established in this work is that in fact the error that we the true error that we attain, like the true error that you see here, in fact asymptotically is dominated by the error of this baseline, right? By the error that we do on the baseline. So in other words, the error that we do, like the fluctuations, remain at the Monte Carlo rate throughout training, okay? Asymptotically as the training goes to infinity, and of course asymptotically as the number of particles goes to infinity. So for those of you who might be familiar with some related work, this is really along the lines of what we call this dynamical central limit theorems, like this propagation of chaos arguments, that date many years ago, like 50 years ago. And in the context of neural networks, have been related results involved is work by Leonic on the context of very, very sparse, like a sparse measure optimization. So there's like very strong assumptions on the target. And so, and here, let me also mention that this control is actually, we can actually prove that the fluctuations totally vanish at the Monte Carlo scale in more strong conditions, right? Like whenever we are interpolating the function without regularization, right? So like that's the case where one has like a, one is able to completely overfit the training data and that without any regularization. And the reason, like the technique behind this proof, is to really understand that this baseline is in fact dominating the dynamic fluctuations through what's called a Volterra kernel. And the whole effort of the proof is establishing that this kernel is actually positive semi-definite, right? So the the errors actually dominate. Okay. And this is just some numerical experiments that illustrate that in fact for when we have like as a target function f star some planted model, right? It's like a real neural network with parameters that are hidden. Then when we try the model, indeed we verify that the fluctuations, once we scale them by the number of units, in fact all stay below this Monte Carlo rate, which is the dashed line here. As usual, the theory is pessimistic, right? Because even in the cases where there's no full interpolation or regularization, the fluctuation, the dynamical fluctuations are below the scale. Okay, so and just another comment on the result. Of course, so the fluctuation result that I just described is still qualitative, right? In the sense that we look at the size of the fluctuations as the number of neurons gets very large, right? So we know that the fluctuations are really at the scale of 1 over square root of the number of neurons, but they are still something that holds qualitatively. So you might ask the question, well, how can we actually bring these results back to something that is actually quantitative, right? That holds in a non-asymptotic sense. So one thing to note is that these kind of like non-asymptotic results, quantitative results, they need to actually coordinate, like they need to be consistent with actually known lower bounds, super polynomial lower bounds. And these are using a framework that is called the statistical query framework. So the idea, that is put forward by these recent works by some people from like Shrubi Goel and Adam Clivens, and then Ilias Diakonikolas and Kane from USC. The idea is really to try to learn functions F star where the neurons, I have placed the neurons in strategically placed locations. And so if I place them in certain adversarially chosen locations, I can actually prove that the number of steps I need for the number of gradient steps I need to be able to approximate this function is probably super polynomial, right? So I need a number of steps that is growing faster than any polynomial with respect to the parameters of the problem. So what we are doing together with my colleague, John Niles-Witt, is to try to understand the generic case by actually following a not so unrelated idea from before, but instead of lifting the problem from the space of parameters of the neural network to the space of measures, empirical measures, is kind of a very brutal lifting, right? We go from a finite dimensional space to infinite dimensional space. Here we are proposing a lifting that is a bit more gentle. So instead of, we are just adding one new dimension to the problem. And this dimension, think it as some parameters of a heat semigroup, of a diffusion semigroup. Right? So for example, we are introducing a landscape where we have the same dimension as we had before, the parameters, but then we are adding a new coordinate, right, for where we can actually potentially move. That it's like a temperature coordinate, right? So at time 0 we have the original landscape, but then the more we go up in this direction, the more we are smoothing, right? So these the solutions of this heat semigroup are just a basic think about this as applying a Gaussian kernel, like a Gaussian smoothing, where the variance of the Gaussian increases with the temperature. And so using this framework, we can obtain some preliminary results that are in the positive side. So if we have again these like planted models and the number of planted neurons is not too large, still here we require we can have number of neurons that diverges with dimension, but still like slower than we think is true. Then we can use a certain variant of gradient descent that is called a Frank-Wolf. Again, if some people is interested, we can discuss about this offline. But think about this as some kind of like an incremental version of gradient descent. We can establish like efficient learning with actually a number of neurons, with a number of student neurons that again is polynomial, is actually linear in dimension. All right. So okay, so this was the part of my talk that was concerning optimization. So in the remaining minutes I have, I'm gonna switch gears, and I'm gonna describe another aspect of this problem that concerns what happens if now we go beyond the space of shallow neural networks. And so the functions that we have seen, that we have studied so far, as I said, they can be written as sums of rich functions. And from what I described also before, we can approximate them efficiently by using a Monte Carlo, right? So Monte Carlo approximation is essentially good enough for this class. And one can do better by doing like approximation schemes that are maybe a bit more deterministic and leveraging a bit more structure of the problem. But just think that one can efficiently approximate the function as long as this function is promised to have a norm that doesn't blow up with dimension. And in fact, one can actually, from what I said before, in fact, this space of shallow neural networks is not too different from just characterizing the regularity of the function in terms of the Fourier decay. And so, not surprisingly, one can control this F1 norm, this variation norm, in terms of properties of the original properties of the Fourier transform of the function. And so, in fact, what here the properties that we need to belong in that space is just some kind of like integrability of the Fourier transform. And so this, and again, this was actually developed again by works of Baron, like already from almost 30 years ago. And so this is actually a property that one can argue that is very strong, right? In a sense, it's like again cursed by dimension, right? Because you know, the decay, you know, here where one is integrating over an exponentially large space, right? So having something that is integrable is pretty strong. And so a natural question is really, okay, can we understand which are the functions that are not well approximated in that space, but one can still approximate well with a deeper architecture? And in particular, we also want to understand whether these conditions are actually necessary. And more importantly, this is also hinting at the fact that we need to understand also this question of approximation benefits, like the approximation benefits of depth in presence of something a bit more structure, not just like thinking about the input as a high dimensional vector. So the approximation benefits of depth is in fact a pretty interesting and rich aspect of the mathematics of deep learning. And so it's a theory that has its roots in the Boolean circuits, in the community of the theoretical computer science that studied like a circuit lower bounds. And so these are like very classic works. And so little by little, some of these questions were kind of ported back to the world of real neural networks. For example, by the work, an important work was by Matus Telgarsky, who really studied like this question by exploring kind of combinatorial properties. For example, if I have a function that has a lot of oscillations, it's more efficient to approximate a lot of oscillations by composing a sawtooth than putting a lot of sawtooth, right? Because when I compose something that oscillates, I get something that I have an exponential gain in how many oscillations I can express. So but maybe a bit more related to our framework, there's these works by Ohad Shamir and Ronen Eldan and Amit Danieli and Safran, who really studied this problem in the high dimensional regime, right? So really they construct functions that had this oscillatory looking behavior, where these functions cannot provably be approximated in F1 in the space of shallow neural nets, but can be efficiently approximated with a deeper neural network, right? So there's and here the important thing is that in one case we are cursed, in the other case we are not. So one of the things that we set out to study with Luca and Sami is can we go beyond these examples of radial functions, right? So what is the nature of these functions, of the functions that where we need depth? And so like an important class of functions that we studied were functions that had this like piecewise structure, right? So like the thing that you would imagine when you have like a ReLU in the middle. So the result that we have, like a lower bound that we obtain, is that if you look at functions f star that have this like piecewise oscillatory behavior, right? So think about the function that oscillates, but it can oscillate with a different frequency at every part of the, at every different region of the space, like a piecewise oscillatory function. So these functions, in fact, we can show that as soon as we have, so there are two properties that are key. So the first one is to have a central frequency that has to grow with dimension, right? So we are asking a question of we are asking the problem of approximating an oscillatory function, and we are kind of making the problem very hard, right? Because we are adding increasing the central frequency with dimension, and we're also measuring error with respect to a data distribution that is heavy tail in the right sense. So in these conditions, we can prove that there's no efficient approximation with a shallow neural network, but in fact, there is an approximation that is efficient with a deeper network. And so the idea of the proof is heavily relying on, again, the harmonic analysis over the d-dimensional space. And the idea of the proof is actually comes mostly from the paper by the original work of Eldan and Shamir. And the idea is really to exploit the fact that what shallow neural networks are able to do is to approximate, again, this Baron property, right? But as soon as the function that we are constructing does not have integrable Fourier transform, in other words, that the Fourier transform energy is kind of too spread over the high dimensional space, then these functions cannot approximate well. The shallow model cannot approximate well. And so here, really, it turns out that this assumption about the heavy tail assumption on the data distribution and the fact that the central frequency increases is actually necessary, in the sense that if we don't have these two properties, then an interesting phenomena comes up, right? So we have, then suddenly we have an efficient upper bound using this shallow model. In the sense now, if I have a function f star that can be expressed as a very as a depth L, like a deep network that is piecewise linear, right? So there's no oscillation, there's no oscillatory behavior, and the reason, and we can control the kind of the size of the oscillations with the norm of the weights. Then, in fact, we can find a shallow neural network that has width that is polynomial in dimension, that has good approximation under a metric that is just like a uniform measure metric on the sphere. So here you don't need to understand the kind of you don't need to understand all the details of the coefficients here, but the point is really that here we have a rate that is polynomial in dimension at the expense of being exponential in the error, right? So in other words, if I wanna decrease the error by half, I might still need to pay, like, to use an exponentially larger number of neurons to approximate. But if I keep the approximation error, like the approximation error target, to be a constant, I just look at what happens as the dimension increases. The number of neurons I need doesn't need to increase exponentially with dimension, right? It can still increase polynomially with dimension. And so this is so as a take home for this kind of like approximation benefits of depth, there's a sort of a mixed feelings, right? So on one hand, we can see that so we can see that actually depth brings an approximation advantage that is a little bit unclear, right? In the sense that the things that are necessary to break the approximation power of shallow neural networks, they involve this like a data distributions that are very heavy-tailed and functions that oscillate a lot, right? In ways that are pretty adversarial. And so, and in fact, in terms of characterizing the approximation properties of the space of shallow neural networks, we can see that actually the intuition of Baron, in fact, is the right one, right? It's like essentially the only thing that you can really approximate well are things that have very large, very fast decay in Fourier. Which and the other thing that I want to mention here that is important is that so far we have discussed separating shallow versus deep, like shallow in saying one hidden layer versus more than one. In fact, it turns out that it's actually pretty hard to extend these techniques to do more general separations. And there's a very nice work by Bardi and Ohad Shamir that really touches on this difficulty. Okay, so what is here? Well, like the keyword here is like unstructured, right? If we look at this problem in generality, it seems that it's not so clear what are the benefits of depth. But in fact, we can now, and this will be the last snippet, we can try to understand what happens as we introduce a bit more structure into the problem, right? And so structure into the problem can mean really going beyond this example of just treating the input as a high dimensional vector. So one very important source of structure comes from, for example, understanding, doing function approximation and learning under known symmetries. And perhaps like the simplest symmetry that one could imagine is the symmetry that comes from like a discrete symmetry of like a permutation invariance. So in other words, the setup is here to think about like a problem where now the input is not just like one high dimensional observation, but it's a collection of points, and each of the points can belong to a domain that can be low dimensional. For example, think about like a particle system, like a system that you observe in physics, or like a leader, right? We have like some measurements here that are like points in 3D. And so what I'm asking here is functions that are agnostic to the order of these points, right? So if I permute the input, I would like to get the same output. And so an important observation is that we can absorb this invariance, like this ambiguity, by expressing, but again, embedding the input, like the input point cloud, into its empirical measure, right? So again, this representation is capturing the fact that we don't care about the order of these points. And so now we can transform the problem of trying to approximate and learn functions defined over kind of this collection of points to functions that are defined over the space of input probability measures of the set, right? So under some conditions, one can really extend functions defined over point clouds to functions defined over probability measures. So how can we actually redo the thing that we described so far when we take the input to be actually a non-Euclidean space that is infinite dimension, right? It seems like we are making our problem harder. But in fact, it turns out that, and this is actually work that is really being done by my student Aaron Zweig. So now we can basically adapt everything we have said so far by just replacing the standard dot products in the Euclidean domain by the appropriate dual forms in the space of measures. So now when we look about the rich function, we can think about the rich function as something as the same thing as before, but instead of this being the Euclidean dot product, now it's basically just testing a measure against a test function phi. So the weights of the neuron are now like test functions. But the same way, we can just define again the shallow neural network as before, and we can still define the infinite wide limit of this model by taking this sum and transform it into an integral. So now we really have naturally emerging like two levels of learning. One that is we need to learn how to find a good domain of test function, right? Because as opposed to the Euclidean case, now we cannot afford to integrate over all the space of test functions, right? Because all the space of test functions is an infinite dimensional space, right? So we would like to first have a first level of feature learning where we find a good domain of functions. And once we have found a good domain of functions, we can use another set of feature learning to select which are the useful features among that space. So it turns out that we can, like the two spaces that I described before, the space that has this adaptivity that is F1 that is larger, and the kernel, which is like the smaller version but easier to understand, we can now combine them in these two levels of the hierarchy. And they give naturally these three spaces, and we have exactly the same kind of a hierarchy that one could imagine, that this space is containing this one, that is containing this one, because every time we go up here in the slide, we get more and more adaptivity. And so we can prove, we can quantify how much do we gain in terms of approximation as we add more and more adaptivity. And we can show that we have, again, like quantitative separation between these spaces. And these spaces, even though they become bigger and bigger, they are still like learnable in the sense that we have generalization bounds, right? Like the generalization bounds that you see here, they are not cursed by dimension. So here we have some experiments, just like kind of verifying these results. And one of the things that we are currently working on that is personally I'm quite excited about is how can we actually adapt these results to deal another important source of symmetry, which is called the anti-symmetry by fermion, which means that every time you apply a permutation, you multiply the function by the sign of the permutation, right? So, and this is a very important source of structure that is used in quantum mechanics to understand basically the wave functions that you need to solve like the Schrodinger equation. They satisfy this form of like fermion antisymmetry. Okay, so just as a conclusion, what I also try to convey here is that there are two main kind of challenges for learning. One that involves like an optimization challenge, and the other that is an approximation challenge. And you might wonder, well, how can I mean, at the end, I want to have both that are good, right? So there's a natural way to combine the two. And so one of the kind of questions that is right now kind of looking forward into the future is to understand how do the approximation benefits need to translate into optimization guarantees, right? So in particular, going back to the depth, to the approximation benefits I talked about, there's a natural hypothesis that emerges that says that, okay, I can think about functions where depth is necessary to have good approximation. And these are, one can think about like strong separation in terms of here functions that if the x-axis here is the depth, unless I have a sufficiently deep network, I'm not going to be able to approximate well. And this class of functions, there's a hypothesis that maybe they are not going to be learnable, right? We can approximate them with a deep network, but we might never be able to learn them efficiently. Instead, what the functions that we can maybe learn efficiently are the functions that have this kind of mild depth separation, right? In the sense that adding layers every time is helping the approximation, but doesn't have this kind of like a strong separation. And more importantly, one of the key takeaways from this talk is that in order to understand the benefits of depth, both at the optimization and generalization and approximation, it's very important to think about the physical structure. And I just, of course, described a very simple source of it, like this permutation symmetry, but there's many things that are still to be included. For example, this like the physical structure coming from the space, right? In the case of convolutions. So with that, I would like just to thank you very much. And of course, here are some references of the works I described, and I'll be happy to answer questions.